The true scale of the universe is a scientific question about distance, size, and proportion, and it begins with how far space extends beyond Earth, and how those distances can be meaningfully described. Astronomers do not approach scale as an abstract mystery, but as a measurable structure built step by step from observation, motion, and light. When we talk about scale, we're talking about how far objects are from one another, how large systems are compared to smaller ones, and how these relationships remain stable even as they become vast. Welcome to AstraFlow. Here science drifts quietly, and understanding comes without effort. If you feel comfortable, you're welcome to leave a calm comment below. Now, let's begin. Scale in the universe is not introduced all at once. It is constructed gradually, starting from what can be directly measured and moving outward only when the previous layer is secure. This approach matters because without stable reference points, large numbers lose their meaning. A distance only becomes understandable when it is connected to something already known. For this reason, the science of cosmic scale always begins close to home, with familiar motion, predictable timing, and physical dimensions that can be verified. At its foundation, scale is about comparison. Scientists compare one distance to another, one mass to another, one orbit to another. The Earth becomes an initial unit not because it is central, but because it is accessible. Its size can be measured directly. Its rotation can be timed. Its orbit can be tracked with precision. These measurements form a baseline that allows all larger distances to be expressed in a structured way. Without this baseline, the universe would be a collection of disconnected magnitudes, too large to relate to one another. When astronomers speak about the universe, they do not imagine a single enormous object. Instead, they describe a nested system of regions. Each region has its own characteristic distances, timescales, and motions. Scale is the framework that keeps these regions from blending into confusion. It allows a clear separation between what belongs to planetary space, stellar space, galactic space, and beyond. Each level remains internally consistent, even as the numbers increase dramatically. An important feature of cosmic scale is that it does not rely on human intuition. Human perception evolved to judge distances on the surface of Earth, across landscapes measured in meters and kilometers. Space operates on scales where those units quickly become impractical. Instead of stretching familiar units endlessly, astronomy introduces new ones when needed. This is not done to complicate understanding, but to preserve clarity. Each new unit marks a transition into a different spatial regime. Before reaching those larger units, however, it is important to recognize that scale is also tied to motion and time. Distance is rarely measured in isolation. It is inferred through how long something takes to move, orbit, or transmit information. Even at the largest scales, motion remains the key. Galaxies rotate, clusters drift, light travels. These movements provide the measurable signals that define size and separation. Without motion, scale would be invisible. The universe does not present itself as a static map. It reveals its structure gradually through repeated observation. Astronomers observe how objects shift position over time, how their light changes, and how their gravitational influence affects nearby matter. From these subtle effects, large distances are derived with remarkable accuracy. Scale, in this sense, is not guessed. It is built through accumulated evidence, refined over generations of measurement. Another essential aspect of scale is that it remains consistent regardless of perspective. The Earth does not become smaller because the universe is large. Instead, Earth retains its measured size while being placed within a larger framework. This consistency allows scientists to move freely between scales without contradiction. A planet can be described accurately, even while being understood as a tiny component of a galaxy. Both descriptions are simultaneously correct. This layered understanding prevents confusion. When discussing the universe, one must always know which scale is being addressed. Are we talking about distances light travels in seconds or in billions of years? Are we describing orbital motion within a star system or the drift of galaxies across cosmic time? Each question belongs to a specific layer, and clarity depends on staying within that layer until it is complete. As we proceed through these layers, the numbers will grow, but the method will remain the same. Observation leads to measurement. Measurement leads to comparison. Comparison leads to structure. At no point is imagination required to fill gaps. The universe's scale is not speculative. It is empirical, grounded in signals that reach us continuously, even now. It is also worth noting that scale does not imply hierarchy or importance. Larger structures are not more significant than smaller ones. They simply operate under different conditions. A molecule, a planet, and a galaxy all follow physical laws with equal precision. Scale changes the context, not the reliability of those laws. This principle allows scientists to apply consistent reasoning across immense differences in size. In this opening section, the goal is not to overwhelm with numbers or distant objects. It is to establish a calm framework for thinking about size and distance in a way that remains steady as the universe expands outward. Once this framework is in place, each additional layer can be introduced without strain. The mind does not need to stretch, it only needs to follow. As the universe unfolds in scale, nothing rushes. Distances do not demand urgency. They simply exist, measured patiently through light, motion, and time. In the next section, we'll begin with the most immediate reference point available to us, grounding the idea of scale in something physically familiar before moving outward again. To understand scale beyond Earth, it helps to first understand Earth itself as a measured object in space. Earth is not a symbolic centre, but a physical reference with known dimensions, mass, and motion. Its radius, its circumference, and its distance from the Sun are values established through centuries of observation and refinement. These measurements are stable, repeatable, and precise, making Earth a reliable starting point for extending scale outward into space. Earth has a diameter of about 12,700 kilometers. This number alone is not especially meaningful until it is used as a comparison. It becomes useful when distances are expressed in terms of how many Earth diameters they span, or how Earth-sized objects behave under gravity. Earth's mass also matters. At roughly 6 sextillion metric tons, it provides a benchmark for understanding how gravity binds matter together at planetary scale. With these values, Earth becomes not just a place, but a unit. Motion adds another layer of reference. Earth rotates once every 24 hours and completes one orbit around the Sun in just over 365 days. These cycles create predictable time intervals that anchor larger measurements. When astronomers observe another object moving in a similar pattern, Earth's motion provides a comparison that allows distance and mass to be inferred. Scale grows outward, but the reference remains steady. The distance between Earth and the Sun is particularly important. Known as 1 astronomical unit, this distance is about 150 million kilometers. Rather than repeating this number constantly, scientists use the astronomical unit as a standard length when describing planetary orbits. It simplifies communication and maintains clarity. When distances remain within the solar system, this unit keeps scale grounded and manageable. From Earth's surface, space may appear empty and uniform, but in measurement terms it is highly structured. Satellites orbit within a few thousand kilometers. The Moon orbits at roughly 30 Earth diameters away. Each of these distances is directly measurable through radar, laser ranging, and orbital mechanics. There is no ambiguity at this level. Scale is confirmed through direct interaction. Earth's gravitational influence also defines a region of space. Objects near Earth follow predictable paths determined by its mass. This region does not extend indefinitely. Beyond a certain distance, the Sun's gravity dominates. This transition marks a natural boundary in scale, separating near-Earth space from solar space. Boundaries like this help organise the universe into zones, each governed by different dominant forces. It is important to notice that even at this early stage, scale is already expanding faster than human travel. While aircraft cross continents in hours, spacecraft take days to reach the moon. This difference introduces the idea that physical distance in space has practical consequences. Time becomes a companion to scale. The farther something is, the longer interaction takes, even with advanced technology. Earth also serves as a reference for density and composition. Its layered structure, from core to crust, informs how planets form and behave elsewhere. When scientists observe rocky exoplanets, they compare their mass and radius to Earth's to determine composition. Scale, here, is not only spatial but physical. Size and mass together reveal internal structure. Despite its usefulness, Earth remains a small object on cosmic terms. This is not a philosophical statement, but a measured one. When placed next to the Sun, Earth becomes a minor component. When placed within the solar system, it becomes one orbit among many. This contextualization is gradual and precise. Nothing is diminished, it is simply located. By anchoring scale to Earth, astronomers ensure that every larger measurement remains connected to something concrete. This prevents numbers from becoming abstract or detached. Even when distances grow beyond direct measurement, their origins trace back to Earth-based reference points, telescopes, and timing systems. As we move outward from Earth in the next section, the distances will increase, but the method will not change. Measurement will still rely on motion, timing, and comparison. The scale will grow, but the foundation will remain calm and stable, allowing understanding to continue without effort. Beyond Earth itself, the next layer of scale is the space immediately surrounding our planet. This region is often described as near-Earth space, and it extends from the upper atmosphere outward through the region, where Earth's gravity remains the dominant influence. Although this space appears vast when viewed from the surface, its scale is still closely tied to Earth's dimensions and motion. Distances here are measured in thousands or tens of thousands of kilometers, remaining within a range that can be directly observed and monitored. Artificial satellites occupy much of this region. Low Earth orbit begins only a few hundred kilometers above the surface. At this altitude, a spacecraft completes an orbit in roughly 90 minutes. The short orbital period reflects the closeness of this space. Earth's gravity remains strong, and objects move quickly to maintain their paths. These tight orbits provide a clear sense of how rapidly scale increases even just above the planet. As altitude increases, orbital periods lengthen. Medium Earth orbit, used by navigation satellites, extends to around 20,000 kilometers above the surface. At this distance, satellites take about 12 hours to circle the planet. The change in timing reflects the increase in distance. Scale is revealed not only by length, but by rhythm. Longer orbits signal larger spaces. Farther still, geostationary orbit lies at approximately 36,000 kilometers above Earth. At this altitude, a satellite's orbital period matches Earth's rotation, allowing it to remain fixed above one point on the surface. This specific distance is not arbitrary. It emerges directly from Earth's mass and rotation rate. The existence of such a stable orbit demonstrates how physical laws shape scale in predictable ways. Beyond artificial satellites, the Moon marks the next major reference point. Orbiting at an average distance of about 384,000 kilometers, the Moon lies roughly 30 Earth diameters away. This distance is large enough that travel times become significant. Even at high speed, spacecraft take several days to reach lunar orbit. This introduces a new sense of separation, one that is no longer immediate or routine. The Moon's orbit also provides critical data for measuring distance. Laser ranging experiments, which bounce light off reflectors placed on the Moon's surface, allow its distance to be measured with centimetre-level precision. This technique demonstrates how light becomes a ruler for space. Even at this scale, measurement remains direct and precise. Between Earth and the Moon, space is not empty. It is filled with the solar wind, faint dust, and the extended reach of Earth's magnetic field. These features are subtle, but measurable. Their presence reminds us that scale includes not only large objects, but also regions of influence. Fields and particles extend far beyond solid surfaces, shaping the environment of near-Earth space. As distance increases, Earth's gravitational dominance gradually weakens. At a point roughly 1.5 million kilometers away, gravitational balance points appear, where Earth's pull and the Sun's pull interact. These regions, known as Lagrange points, form natural locations for spacecraft. Their existence illustrates how scale creates structure even in empty space. At this stage, distances are still small enough to be visualized through comparison with Earth. The Moon's orbit, while vast compared to terrestrial distances, fits comfortably within a mental framework built from Earth's size. This containment allows understanding to remain steady. The mind does not need to leap. It simply follows the expansion outward. Near-Earth space represents a complete layer of scale. It has clear boundaries, predictable motion, and direct measurement methods. It is the final region where Earth remains the primary reference for distance and gravity. Beyond this, a transition occurs. The Sun becomes the central influence, and a larger system begins to take shape. As we move forward, Earth will remain part of the picture, but it will no longer define the centre. The scale will shift smoothly into the structure of the solar system, where distances grow by orders of magnitude, yet remain governed by the same calm physical laws. Beyond the space dominated by Earth's gravity, the scale of the universe opens into the structure of the solar system. Here, the Sun becomes the central reference point, and distances expand outward in a steady, organised way. The solar system is not a vague region of scattered objects. It is a gravitationally bound system with defined zones, each marked by characteristic distances and orbital patterns. Closest to the Sun are the inner planets, moving along paths measured in fractions of an astronomical unit. Mercury orbits at an average distance of about 4/10 of an astronomical unit, completing a circuit in less than 3 months. Venus follows at roughly 7/10 of an astronomical unit, and Earth at 1. These distances are small enough that light takes only minutes to cross them, yet large enough that direct travel requires months with current propulsion. Scale here becomes both spatial and temporal. Mars marks the outer edge of the inner planetary region at about 1.5 astronomical units. Beyond Mars lies the asteroid belt, a wide region of rocky debris spread across hundreds of millions of kilometers. Despite common imagery, this belt is not densely packed. The average separation between objects is vast. Scale here is defined not by crowding, but by emptiness. The belt occupies a large volume yet contains relatively little mass. The gas giants introduce another expansion of scale. Jupiter orbits at about 5 astronomical units from the Sun. Its mass exceeds that of all other planets combined, and its gravitational influence shapes much of the solar system. The distance from the Sun to Jupiter is great enough that sunlight takes over 40 minutes to arrive. This delay is a measurable signal of scale, reinforcing the growing separation between regions. Saturn, Uranus, and Neptune extend the planetary system outward to about 30 astronomical units. At Neptune's orbit, sunlight takes 4 hours to reach the planet. Orbital periods lengthen dramatically. Neptune requires more than 160 years to complete a single orbit. Time and distance continue to stretch together, revealing scale through rhythm as much as through length. Beyond the planets lies the Kuiper Belt, a disk of icy objects extending from roughly 30 to 50 astronomical units. Pluto and similar bodies inhabit this region. Although small individually, these objects collectively define a broad outer zone. Their orbits are slower and more inclined, reflecting the weaker gravitational binding at these distances. Farther still, the Oort cloud represents the outermost known boundary of the solar system. This spherical cloud of icy remnants may extend tens of thousands of astronomical units from the Sun. At these distances, the Sun appears as a bright star rather than a dominant disk. Objects in the Oort cloud move so slowly that a single orbit may take millions of years. Scale here becomes immense yet remains gravitationally connected. It is important to note that the solar system's edge is not a sharp boundary. Gravitational influence fades gradually, overlapping with the gravitational fields of nearby stars. This transition region illustrates how scale layers blend smoothly rather than ending abruptly. Systems are defined by dominance, not by walls. Within the solar system, measurement remains grounded in orbital mechanics and light travel time. Distances are inferred from motion, timing, and gravitational interaction. Even at the farthest reaches, the same methods apply. Scale grows, but the science remains consistent. This complete structure, from the Sun's surface to the distant Oort cloud, forms a self-contained layer of cosmic scale. It is large enough to challenge intuition, yet small enough to remain connected through direct measurement. Beyond it lies another transition, where the distances between stars become the dominant feature. In the next section, we will step beyond the solar system entirely, entering the space between stars, where new units and new perspectives become necessary to maintain clarity. Once the solar system is fully established as a complete structure, the next step outward requires a change in how distance is expressed. Kilometers and even astronomical units become impractical when the separation between objects grows far larger than any planetary orbit. At this point, scale becomes inseparable from light itself. Distance is no longer described primarily by length alone, but by how long light takes to travel from one place to another. Light moves at a constant speed in a vacuum, roughly 300,000 kilometers per second. This speed is not approximate in scientific terms, it is a fixed value that underpins modern measurement. Because it does not vary, light becomes a reliable ruler for space. When astronomers speak of distance beyond the solar system, they often do so in terms of light travel time, because this directly connects separation with observation. Within the solar system, light time distances are still relatively short. Sunlight reaches Earth in just over 8 minutes. Light from the Sun reaches Jupiter in about 40 minutes and Neptune in around 4 hours. These delays are measurable and routinely accounted for in spacecraft communication. They mark a gradual transition toward larger scales, preparing the mind for distances that will soon exceed hours and days. As the solar system fades into the background, the nearest stars appear. These stars are not separated by a few astronomical units, but by tens of thousands. Expressing these distances in kilometers would produce numbers too large to be meaningful in everyday use. Instead, astronomers define a new unit based on light's motion over longer intervals. 1 light year is the distance light travels in 1 year, moving continuously at its constant speed. A light year is a unit of distance, not time. This distinction is important and remains consistent throughout astronomy. When we say a star is 4 light years away, we are stating how far light must travel, not how long the star exists. This framing keeps scale grounded in observation. Distance becomes something directly tied to what is seen and when it is seen. Even before reaching full light years, smaller light-based units are sometimes used. Light seconds, light minutes, and light hours all appear naturally as distances increase. These units maintain continuity. There is no sudden leap from planetary space to interstellar space. The scale stretches smoothly, guided by the same constant speed. Using light as a measurement tool also introduces a subtle shift in perspective. Observing distant objects means observing them as they were when their light began its journey. This is not an abstract concept, it is a direct consequence of distance. The farther something is, The older the information we receive, scale and time become linked through observation without any philosophical implication. Despite this connection, measurement remains precise. Astronomers use techniques such as parallax, where the apparent position of a nearby star shifts slightly as Earth orbits the Sun. This tiny shift, measured against distant background stars, allows distance to be calculated. The method relies on geometry and motion, not assumption. Light carries the information, but structure provides the solution. As distances increase further, additional methods supplement parallax. Brightness comparisons, spectral analysis, and standard reference objects all contribute to refining scale. Each method is calibrated against closer, better-known distances. This layered approach ensures that even the largest measurements remain connected to smaller, verified ones. Light-based distance does not replace earlier units, it extends them. Astronomical units remain useful within planetary systems, while light years take over between stars. Each unit belongs to its appropriate scale. Clarity is preserved by choosing the unit that best matches the region being described. In this way, light becomes more than illumination. It becomes the medium through which scale is revealed. It carries position, motion, and distance across vast separations, allowing the universe to be measured without direct contact. As we move forward, these light-defined distances will guide us into the space between stars, where separation itself becomes the dominant feature. With light now established as the primary tool for measuring large distances, we move into the region between stars. This is interstellar space, and its defining feature is separation. Stars are not clustered closely together, even within a single galaxy. Instead, they are spaced at distances that make planetary systems appear tightly packed by comparison. Understanding this spacing is essential for grasping the next layer of cosmic scale. The nearest star system to our own is Alpha Centauri. Located a little over 4 light-years away, this distance is often described as close in astronomical terms, yet it represents a separation of more than 40 trillion kilometers. At this scale, even light takes years to cross the gap. Spacecraft traveling at current speeds would require tens of thousands of years to reach such a destination. This is not a limitation of technology alone, but a direct expression of scale. Stars within the local region of the galaxy are typically separated by several light-years. In denser regions, such as star clusters, distances may shrink to fractions of a light-year, while in sparse regions they may expand further. Even so, collisions between stars are extremely rare. The volume of space between them is vast, and motion unfolds slowly. Interstellar space is defined more by emptiness than by objects. To describe distances between stars, astronomers often use another unit alongside the light-year, called the parsec. A parsec is based on geometric measurement using Earth's orbit as a baseline. 1 parsec equals about 3.26 light-years. While the definition is technical, its purpose is practical. It allows distances to be calculated directly from observed angles. Like other units, it exists to maintain clarity rather than complexity. Within a few dozen light-years of the Sun, hundreds of stars are known. This local neighbourhood forms a small sample of the galaxy as a whole. By mapping the positions and motions of these nearby stars, astronomers can study how stars move within the larger galactic structure. Scale here is revealed not only through distance but through collective motion. Interstellar space is not entirely empty. It contains thin clouds of gas and dust known as the interstellar medium. These materials are sparse but spread across enormous volumes. Over time, they become the raw material for new stars and planetary systems. Even at this low density, their presence affects how light travels and how gravity shapes regions of space. The temperature of interstellar space is low, only a few degrees above absolute zero. Energy is spread thinly across large distances. Processes unfold slowly. This calm, extended environment contrasts sharply with the dense and active regions near stars. Scale influences not only size but pace. Larger regions evolve more gradually. From within interstellar space, the solar system occupies a tiny bubble carved out by the sun's wind. This bubble, known as the heliosphere, extends far beyond the planets but remains small compared to the distances between stars. Its boundary marks the transition from solar influence to galactic influence, another smooth shift in scale rather than an abrupt one. As we consider the space between stars, it becomes clear that galaxies are not dense collections of objects, but vast frameworks with long separations. The distances that define interstellar space prepare us for the next step outward, where individual stars blend into larger patterns and the galaxy itself becomes the primary structure. In the next section, we will shift from the space between stars to the structure that contains them all, examining the Milky Way as a complete system measured in tens of thousands of light years. When individual stars are viewed together rather than in isolation, they form a larger structure known as a galaxy. Our home galaxy, the Milky Way, contains hundreds of billions of stars distributed across a region of space far larger than the distances between nearby stellar systems. At this scale, light years become the natural unit, and distances are measured in tens of thousands rather than single digits. The Milky Way is a disc-shaped galaxy with a diameter of roughly 100,000 light-years. This disk is not thin. It has a thickness of several thousand light-years, with most stars concentrated toward the central plane. From above, it would appear as a flattened spiral, with arms extending outward from a dense central region. These arms are not rigid structures, but regions where stars and gas are more concentrated. At the centre of the galaxy lies a dense bulge of stars, surrounding a supermassive black hole. This central region spans several thousand light-years and contains stars that orbit much closer together than those in the outer disk. Motion here is faster, and gravitational influence is stronger. The scale of this region is large by planetary standards, yet small compared to the galaxy as a whole. Surrounding the disk is a diffuse halo of stars and globular clusters. This halo extends tens of thousands of light-years beyond the visible disk. The stars here are older and more sparsely distributed. Their orbits are elongated and inclined, moving above and below the galactic plane. The halo adds depth to the galaxy's structure, transforming it from a flat disk into a three-dimensional system. The Sun is located within one of the Milky Way's spiral arms, roughly 26,000 light-years from the galactic centre. At this distance, the Sun completes one orbit around the galaxy in about 230 million years. This timescale reveals another aspect of scale. Galactic motion unfolds far more slowly than planetary motion, yet remains orderly and predictable. Within the Milky Way, stars follow curved paths determined by the combined gravitational influence of all the mass in the galaxy. This includes not only visible stars and gas, but also a large component of unseen mass that affects rotation. By measuring how fast stars orbit at different distances from the centre, astronomers infer the galaxy's overall mass distribution. Scale is again revealed through motion. Despite containing enormous numbers of stars, the Milky Way remains mostly empty space. The average separation between stars within the disk is still several light-years. The galaxy's vast size comes from the accumulation of these separations, repeated billions of times. Density remains low, even as total mass grows large. Light takes 100,000 years to cross the Milky Way from edge to edge. This means that when observing distant regions of the galaxy, we're seeing them as they were tens of thousands of years ago. Even within a single galaxy, distance introduces time delay. Scale and observation remain linked. The Milky Way is not isolated. It is one of many galaxies, each with its own structure and scale. Understanding our galaxy as a complete system prepares us to step beyond it, where distances between galaxies become the defining feature of the next layer. As the focus shifts outward, individual stars fade into collective light, and galaxies themselves become the primary objects of measurement. In the next section, we will explore the space between galaxies, where scale expands once again and new structures emerge. Within the Milky Way, motion is constant but unhurried, and understanding this motion helps clarify the galaxy's scale. Stars do not remain fixed within the disk. They orbit the galactic center, guided by the combined gravitational influence of all the mass contained within the galaxy. This motion provides one of the most direct ways to measure the galaxy's size and mass, without needing to observe every star individually. Stars closer to the galactic center complete their orbits more quickly than those farther out. Near the center, orbital periods can be tens of millions of years, while at the Sun's position, one full orbit takes more than 200 million years. At the outer edges of the disk, a single orbit may take several hundred million years. These long periods reflect the vast distances involved. Time stretches naturally as scale increases. By measuring the speed of stars at different distances from the center, astronomers construct what is known as a rotation curve. This curve shows how orbital velocity changes across the galaxy. If mass were concentrated only in the visible stars, orbital speeds would decrease with distance. Instead, they remain relatively constant, revealing the presence of additional mass spread throughout the galaxy. Scale here is inferred from consistent motion across large distances. This extended mass distribution gives the Milky Way a gravitational reach far beyond its visible edge. Stars in the halo and distant globular clusters remain bound, even at tens of thousands of light-years from the center. The galaxy's influence fades gradually, not abruptly. This smooth decline reinforces the idea that scale boundaries in space are zones of transition rather than sharp lines. The motion of stars also reveals the galaxy's overall stability. Despite ongoing formation and evolution, the Milky Way maintains its structure over billions of years. Spiral arms persist as regions of density rather than fixed shapes. Stars pass through them, orbiting independently. Scale does not imply rigidity. Large systems remain dynamic while retaining long-term form. Gas and dust within the galaxy follow similar orbital paths, but with additional complexity. Clouds can collide, compress, and form new stars. These processes occur within the same gravitational framework that governs stellar motion. Even creation and change are constrained by scale. Larger structures provide the context in which smaller events unfold. From our position inside the galaxy, measuring these motions requires careful observation. Astronomers track shifts in spectral lines, measure proper motion across the sky, and compare positions over decades. Each small measurement contributes to a larger map of galactic dynamics. Scale emerges from accumulation rather than single observation. Although galactic motion is slow, it is continuous. Over millions of years, the positions of stars change significantly. Over billions, the galaxy itself evolves. Yet these changes occur at a pace far removed from daily experience. This contrast in timescale is another expression of scale. Larger systems move more slowly, not because they are static, but because their dimensions are vast. Understanding motion within the Milky Way completes our picture of the galaxy as a stable, measurable structure. It also prepares us to compare it with other galaxies, where similar motions reveal both similarities and differences in scale and mass. In the next section, we will turn our attention outward to nearby galaxies, examining how their sizes and distances relate to the Milky Way within a larger cosmic neighbourhood. Beyond the boundaries of the Milky Way, the universe opens into a wider neighbourhood populated by other galaxies. These galaxies are not scattered randomly. They occupy space in a structured way, separated by distances far larger than those between stars, yet close enough to influence one another through gravity. At this scale, individual stars are no longer the focus. Entire galaxies become the units of measurement. The nearest large galaxy to the Milky Way is the Andromeda Galaxy, located a little over 2.5 million light-years away. This distance is immense compared to the size of our galaxy itself. Light takes millions of years to cross the space between them. Even so, Andromeda is considered close in cosmic terms. This illustrates how scale continues to expand, redefining what proximity means at each level. Andromeda is similar in size to the Milky Way, containing hundreds of billions of stars and spanning more than 100,000 light-years. When viewed together, these two galaxies dominate the local region of space. Their sizes and masses allow astronomers to compare galactic structures directly, using one as a reference for the other. Scale here becomes comparative rather than absolute. Surrounding these large galaxies are smaller ones, often called satellite galaxies. The Milky Way has dozens of such companions, ranging from dwarf galaxies with a few million stars to slightly larger systems with more complex structure. These satellites orbit the Milky Way over billions of years, tracing long, slow paths shaped by gravity. Their presence reveals how galaxies grow and interact over time. Distances between galaxies are measured using light-based methods refined over decades. Certain types of stars and stellar events have known brightness, allowing their distance to be calculated by comparing how bright they appear from Earth. These methods extend the same principles used for nearby stars, carefully scaled upward. Each new distance builds upon earlier, closer measurements. Intergalactic space, the region between galaxies, is even more sparse than interstellar space. Matter exists primarily as thin gas spread across enormous volumes. The density is so low that individual atoms may be separated by meters or more. Yet over millions of light-years, this material contributes to the overall mass and structure of the universe. Galaxies are not static relative to one another. They move through space, drawn together or apart by gravity and cosmic expansion. The Milky Way and Andromeda, for example, are slowly approaching each other. This motion is measured through shifts in the light they emit. Even across millions of light-years, motion leaves a detectable signature. Despite these interactions, galaxies remain distinct systems. Collisions between them unfold over hundreds of millions or billions of years, with stars largely passing by one another due to the vast separations involved. Scale ensures that even dramatic events occur gradually, governed by long timescales. By studying nearby galaxies, astronomers gain perspective on what is typical and what is unique. The Milky Way becomes one example among many, its properties placed in context rather than isolation. Scale here provides comparison, allowing patterns to emerge without interpretation or judgment. As we step further outward, these neighbouring galaxies begin to cluster together, forming larger groupings bound by gravity. In the next section, we will explore these groupings, where scale increases again and individual galaxies become components of even larger structures. When galaxies are viewed not just as neighbours but as members of shared structures, they form what astronomers call galaxy groups and clusters. At this scale, gravity operates across millions of light-years, binding dozens, hundreds, or even thousands of galaxies together. The distances involved are far larger than those between individual galaxies, yet the connections remain measurable and consistent. The Milky Way and Andromeda belong to a small association known as a galaxy group. This group spans several million light-years and contains more than 50 known galaxies. The distances between members are large, but gravity acts over these spans with steady influence. Motion within the group unfolds slowly, with galaxies orbiting a shared centre of mass over billions of years. Larger than groups are galaxy clusters. These are among the most massive structures in the universe that are held together by gravity. A typical cluster may contain hundreds or thousands of galaxies and extend across 10 million light-years or more. Within clusters, galaxies move at high speeds relative to one another, often thousands of kilometers per second, reflecting the deep gravitational well created by the cluster's combined mass. Most of a cluster's mass does not come from visible stars, Instead, it is dominated by hot gas and unseen matter that fills the space between galaxies. This gas emits X-rays, allowing astronomers to map the cluster's shape and extent. Once again, scale is revealed through indirect observation. The structure becomes visible through its effects rather than its appearance. Distances within clusters are large enough that light takes millions of years to travel from one side to the other. Despite this, clusters behave as unified systems. Galaxies remain bound, tracing elongated paths through the cluster's interior. Over time, interactions between galaxies and the cluster environment alter their shapes and star formation, showing how scale influences evolution. Between clusters lie regions of lower density, where galaxies are more sparsely distributed. These regions are not empty, but the gravitational pull is weaker. The universe at this scale begins to show contrast, with dense nodes connected by more diffuse surroundings. Structure emerges through variation rather than uniformity. Galaxy groups and clusters form over long periods. They grow as smaller groups merge, guided by gravity acting across expanding space. This process is gradual and continuous. There is no single moment when a cluster appears fully formed. Scale increases through accumulation, not sudden change. Observing clusters also allows astronomers to test measurements of distance and mass at very large scales. The motions of galaxies within clusters, combined with the temperature of the hot gas, provide multiple ways to estimate total mass. When these independent methods agree, confidence in the scale increases. At this level, the universe begins to resemble a network rather than isolated systems. Individual galaxies are no longer the primary units of organization. Instead, they become components of larger assemblies, each with its own internal dynamics and boundaries defined by gravity. As we move outward again, these clusters themselves will begin to connect, forming even larger patterns. The next section will explore how clusters are arranged across the universe, revealing structure on the largest observable scales. When galaxy clusters are viewed together across even larger distances, a broader pattern begins to appear. Clusters are not evenly scattered through space. Instead, they trace long chains and intersections, forming an immense structure often described as the large-scale structure of the universe. At this level, scale reaches hundreds of millions of light years, and individual galaxies and clusters become points within a much larger arrangement. These vast patterns are revealed by mapping the positions of thousands of galaxies across the sky. When their distances are plotted in 3 dimensions, dense regions emerge where clusters gather, separated by wide, low-density regions known as voids. The result is a network-like distribution, where matter forms filaments and walls surrounding enormous empty spaces. This structure is not imposed. It emerges naturally from gravity acting over long periods. The filaments themselves can extend for hundreds of millions of light years. Along these filaments, galaxy clusters and groups are strung together like beads, connected by faint bridges of gas and unseen mass. Within the filaments, gravity is slightly stronger, guiding matter inward over time. Scale here is defined not by compact objects, but by extended alignment across immense distances. Voids occupy most of the universe's volume. These regions can span tens of millions of light years and contain very few galaxies. Their existence is not accidental. As matter flows toward denser regions under gravity, it leaves behind these large, relatively empty spaces. The contrast between filaments and voids is one of the defining features of cosmic scale at this level. Despite their size, these structures are not static. Over billions of years, filaments slowly evolve, clusters grow more massive, and voids expand. The pace of change is extremely slow, but measurable when comparing observations across large samples. Scale once again influences time. The larger the structure, the longer its characteristic evolution. The arrangement of matter on these scales is influenced by conditions set early in the universe's history. tiny differences in density present when the universe was very young were amplified over time by gravity. What begins as subtle variation becomes, over billions of years, a vast network. This process requires no guiding pattern beyond physical law. Scale emerges through repetition and accumulation. Observationally, mapping such large regions requires surveys that measure both position and distance for millions of galaxies. Light from these galaxies carries information about their motion and composition, allowing astronomers to determine how far away they are. Each data point contributes to a larger picture, where scale is revealed statistically rather than individually. At this level, it becomes clear that the universe does not have a preferred directional centre. The network appears similar in all directions when viewed over sufficiently large volumes. Dense regions and voids repeat with comparable sizes and distributions. This uniformity on large scales is a measured property, not an assumption. It provides a stable framework for understanding cosmic expansion. The distances involved in this layer are so large that light from some regions has been travelling for hundreds of millions or even billions of years. Observing these structures is also observing deep into the past. Yet the structures themselves persist across these timescales, changing slowly enough that their overall form remains recognisable. By reaching this level of scale, the universe becomes less about individual objects and more about distribution. Matter organises itself into patterns governed by gravity and expansion, spanning distances far beyond any single system. The mind does not need to hold every detail. It only needs to recognise that structure continues to exist, even as scale grows immense. In the next section, we will approach the outer limit of what can be observed, where distance is defined not by structure alone, but by the finite speed of light and the age of the universe itself. At the largest distances we can measure, scale is no longer defined by clusters or filaments alone, but by a fundamental observational limit. This limit is known as the observable universe. It is not a physical boundary in space, and it is not an edge that matter reaches and stops. It is simply the farthest distance from which light has had time to reach us since the universe began expanding. Because light travels at a finite speed, observation always involves delay. The farther away an object is, the longer its light takes to arrive. When astronomers look deep into space, they are also looking deep into time. There comes a point where light from more distant regions has not yet reached Earth, not because those regions do not exist, but because the universe has not existed long enough for their light to arrive. The observable universe has a radius of about 46 billion light-years. This number may seem surprising, because the universe itself is about 13.8 billion years old. The reason the observable radius is larger than the age in light-years is that space itself has been expanding while light was travelling through it. As light moves, the space between its source and the observer stretches, increasing the final distance. This expansion does not mean that light travels faster than its constant speed. Instead, it reflects the fact that distance is not fixed while light is in transit. The measurement of the observable universe accounts for this continuous stretching. Scale at this level includes both motion through space and the growth of space itself, carefully separated and measured. The observable universe contains all the galaxies, clusters, filaments and voids that we can detect with current instruments. Beyond this region, the universe likely continues, but without observable signals. Its properties remain unmeasured. Science remains precise by limiting claims to what can be observed. Scale is defined by evidence, not assumption. Within the observable universe, matter appears distributed in a statistically similar way in all directions when viewed over very large distances. This observation supports the idea that, on the largest scales, the universe is uniform. Local variations exist, but they average out across immense volumes. This uniformity provides a stable reference for measuring expansion and distance. The boundary of the observable universe is not static. As time passes, light from slightly more distant regions continues to arrive, extending what can be observed. At the same time, cosmic expansion causes some distant regions to move away faster than light can bridge, placing them permanently beyond observation. These two effects operate together, shaping the limits of what can be known. It is important to remain grounded at this scale. The observable universe is not a container holding everything. It is a sphere of visibility centered on the observer, defined by light travel time. A different observer elsewhere in the universe would have a different observable region, centered on their own position. Scale here is relative to observation, not position. Despite its immense size, the observable universe remains measurable. Astronomers use background radiation, galaxy surveys, and precise models of expansion to determine its extent. Each method cross-checks the others, ensuring consistency. Even at this extreme scale, understanding remains structured and calm. Reaching this layer completes the outward journey of scale in space. Distance has expanded from planetary orbits to the limits of observation, guided at every step by measurement and evidence. From here, the perspective begins to shift gently, not further outward, but into how scale interacts with time itself. In the next section, we will explore how distance and time are woven together across the universe, not as abstraction, but as a direct result of observation and motion. At the largest scales, distance cannot be separated from time. This is not a metaphorical connection, but a direct consequence of how information travels through space. Every observation is delayed by the time it takes light to reach us. As distance increases, this delay becomes significant, and the universe reveals itself not as a single moment, but as a layered record of different times observed simultaneously. When we observe nearby objects, such as planets or nearby stars, the time delay is short. The light we receive left its source minutes, hours, or years ago. At greater distances, the delay stretches into millions or billions of years. A distant galaxy is seen not as it is now, but as it was long before Earth existed. Distance, in this sense, becomes a timeline written across space. This relationship allows astronomers to study the history of the universe directly. By observing objects at different distances, they observe different stages of cosmic development. Nearby galaxies show mature structures, while distant galaxies appear smaller, less organized, and more active. This progression is not inferred from theory alone. It is visible in the data. Arranged naturally by scale, the expansion of the universe strengthens this connection. As space expands, light travelling through it experiences a stretching of its wavelength. This effect, known as redshift, increases with distance. By measuring how much a galaxy's light has been stretched, astronomers determine how far away it is, and therefore how long its light has been travelling. Time becomes encoded in colour and spectrum. This encoding allows distance and time to be measured together. A higher redshift indicates greater distance and earlier cosmic time. The measurement is precise and repeatable. Large surveys of galaxies create maps where position and age are linked, revealing how structures evolve across billions of years. Scale provides the ordering principle. At the earliest observable distances, light comes not from galaxies but from a nearly uniform background of radiation. This background represents the universe when it was much younger and denser. Observing it is equivalent to looking back almost to the beginning of cosmic expansion. Time here is not abstract. It is embedded in the distance itself. As scale increases, the time intervals between observable layers also increase. Small-scale structures change quickly, while large-scale structures evolve slowly. A star may change significantly over millions of years, while a galaxy cluster changes over billions. This difference in pace is not accidental. It follows directly from size and separation. Larger systems require more time to reorganize. This layered view of time allows the universe to be studied as a continuous process rather than a single snapshot. There is no need to imagine earlier states, they are already present in observation, arranged by distance. The farther the light has travelled, the earlier the state it reveals. Scale becomes a quiet archive of cosmic history. Importantly, this does not imply that the universe has a preferred present moment. What is seen depends on where and when the observation is made. Each location in the universe has its own visible history, shaped by light travel time. Scale and time remain linked to observation, not to any absolute frame. Understanding this relationship brings stability rather than confusion. Distance is no longer just separation, it becomes a structured way to read change. The universe does not rush forward, it unfolds steadily, with its path still visible across space. In the next section, we will look at how the larger structures maintain stability over long periods, despite expansion and change, and how scale influences the pace of cosmic evolution. As the universe expands and evolves, its larger structures change at a pace set by their immense scale. While small systems can transform relatively quickly, large-scale structures exhibit a remarkable stability over billions of years. This stability is not static. It arises from the balance between gravitational attraction and cosmic expansion, acting across vast distances. Galaxy clusters, filaments, and voids evolve slowly because the forces involved operate over millions of light years. Gravity draws matter inward, while expansion increases separation between distant regions. At certain scales, these effects counterbalance in a way that preserves overall structure. Clusters remain bound, filaments persist, and voids continue to exist as low-density regions. Scale determines which forces dominate. The expansion of space does not tear apart structures that are already gravitationally bound. Within galaxies and clusters, gravity overcomes expansion, keeping systems intact. This distinction is important. Expansion becomes significant only at larger separations, where gravitational binding is weaker. Scale sets the threshold between cohesion and separation. Because of this, the universe develops a layered behaviour. Small-scale systems follow local dynamics, while large-scale systems follow global expansion. Neither overrides the other. They coexist, each operating within its appropriate range. This coexistence allows the universe to grow without losing its internal organisation. Observations across different distances show that the overall pattern of large-scale structures remains similar for billions of years. While individual galaxies merge or evolve, the network of clusters and filaments persists. This persistence reflects the slow pace of change at these scales. Evolution does not erase structure, it reshapes it gradually. Simulations of cosmic evolution support this observational picture. Starting from early density variations, gravity amplifies structure over time while expansion stretches space. The result is a universe that becomes more structured locally while continuing to expand globally. Scale governs the balance between these processes. Time at this level is measured in billions of years. These long intervals allow systems to settle into stable configurations. Sudden changes are rare. Even major events such as galaxy mergers unfold over hundreds of millions of years. Scale ensures continuity. This slow evolution contributes to the uniformity observed at the larger scales. Over immense volumes, differences average out. The universe appears similar in all directions and locations when viewed broadly. This uniformity is not perfect, but it is consistent enough to serve as a foundation for cosmological models. Understanding stability across scale helps clarify why the universe does not appear chaotic. Despite containing countless moving parts, its large-scale behaviour remains orderly. Laws of physics apply consistently, and scale determines how their effects accumulate. As this perspective settles, attention can gently shift from the mechanics of stability to the methods used to observe and measure such vast structures. In the next section, we will focus on the tools and limits of human measurement at extreme scales, staying grounded in observation. At extreme scales, understanding depends not only on what exists, but on how it can be measured. Human perception cannot directly grasp distances measured in millions or billions of light years, so observation relies on instruments and methods that extend the senses without altering the underlying principles. These tools do not change the universe. They translate its signals into forms that can be analysed with care and consistency. Telescopes are the most familiar of these tools, but their role at large scale is not simply magnification. They collect light over long periods, allowing faint signals from distant regions to accumulate. This collected light carries information about distance, motion, composition, and age. Each photon arrives with a history encoded in its wavelength and direction. Measurement at large scale often begins with brightness. If an object's intrinsic brightness is known, its distance can be inferred by how dim it appears. This method relies on reference objects whose properties are well understood. These references are calibrated using closer measurements, forming a chain that links nearby space to the farthest observable regions. Scale is extended step by step without gaps. Spectroscopy adds another layer. By splitting light into its component wavelengths, astronomers identify chemical signatures and measure shifts caused by motion and expansion. These shifts provide precise distance indicators at scales where geometry alone is insufficient. The method remains grounded in physics measured on Earth, applied consistently across space. No single measurement stands alone. Distances are cross-checked using multiple techniques, each with different assumptions and sensitivities. Agreement between methods strengthens confidence. Discrepancies prompt refinement. Scale is not assumed correct. It is tested repeatedly. There are limits to measurement, and these limits are acknowledged rather than avoided. Beyond certain distances, signals become too faint or too stretched to analyse reliably. At that point, science stops extending claims and remains within observable bounds. This restraint maintains clarity. Scale remains defined by evidence, not by speculation. Even within these limits, measurement continues to improve. Advances in detectors, computing, and survey design steadily refine distance estimates. The overall framework of scale remains stable, while its resolution sharpens. Understanding deepens without requiring reinterpretation of fundamental structure. It is also important to recognize that measurement does not require completeness. The universe does not need to be fully mapped to be understood in scale. Sampling across large regions reveals consistent patterns that hold across the whole. Scale emerges from representative observation rather than exhaustive cataloguing. As instruments observe farther and more precisely, they reinforce the continuity of scale. There are no sudden breaks where measurement fails entirely. Instead, there is a gradual fading of detail. Structures remain detectable even as individual components blend together. This measured approach allows scale to remain calm and coherent. Each distance is anchored to observation. Each extension is justified. Nothing is rushed, and nothing is forced. Understanding grows outward at the same steady pace as observation itself. With this grounding in measurement, attention can now widen gently to patterns that repeat across different scales, not as symbols, but as structural similarities governed by the same physical principles. Across the vast range of distances we've explored, from planetary space to the largest observable structures, certain patterns appear again and again. These patterns are not exact repetitions, and they are not symbolic. They are structural outcomes that emerge when the same physical laws operate over different scales. Recognizing them does not require interpretation, only careful observation. One recurring pattern is clustering. Matter rarely distributes itself evenly. Instead, it gathers into concentrations separated by regions of lower density. At small scales, this appears as planets forming from disks of material around stars. At larger scales, stars form in clusters, galaxies form in groups, and galaxy clusters connect into filaments. The mechanism remains gravity, acting wherever matter is present, regardless of size. Another pattern is orbiting motion. Objects bound by gravity tend to follow curved paths around a shared centre of mass. This is seen in moons orbiting planets, planets orbiting stars, stars orbiting galactic centres, and galaxies orbiting within clusters. The speeds and periods change dramatically with scale, but the structure of the motion remains consistent. Curvature replaces straight-line travel wherever binding occurs. Separation is also a consistent feature. As systems grow larger, the average distance between their components increases. Stars are far apart within galaxies. Galaxies are far apart within clusters. Clusters are separated by immense voids. Density decreases as scale increases, even while total mass grows. This pattern allows large structures to exist without becoming crowded or unstable. Timescale follows size in a predictable way. Small systems change quickly. Large systems change slowly. This is not a rule imposed from outside, but a direct consequence of distance and mass. Signals take longer to cross large systems. Forces act over longer paths. Reorganization requires more time. Scale sets the pace. Boundaries between systems also show similarity. They are rarely sharp edges. Instead, influence fades gradually. A planet's gravity weakens with distance. A star's influence blends into the galactic field. A galaxy's boundary merges into the gravitational environment of a group or cluster. This gradual transition appears at every level, reinforcing continuity. Even emptiness follows a pattern. What appears empty at one scale often contains structure at a smaller one. Interstellar space contains gas and dust. Intergalactic space contains diffuse matter and radiation. Voids contain fewer galaxies, but they are not entirely empty. Scale determines what is visible, not what exists. These recurring features do not imply uniformity. Each scale has unique conditions, materials, and histories. What repeats is the way structure arises, not the structure itself. The same laws operate everywhere, producing different outcomes depending on a scale and context. Observing these patterns helps stabilize understanding. Scale no longer feels like an endless increase in size, but a progression through familiar organizational principles applied over larger distances and longer times. The universe does not become more chaotic as it grows larger. It becomes more spacious, more gradual, and more distributed. With this recognition, attention can soften slightly. The universe's scale is no longer just a sequence of expanding distances. It is a continuous framework where structure, motion, and change remain coherent at every level. In the next section, we will gently place human observation within this framework, not to elevate or diminish it, but simply to note where it fits within the measured structure we have been exploring. Within the vast framework of scale that extends from Earth to the limits of observation, human presence occupies a very small and specific region. This placement is not symbolic and does not require interpretation. It is simply a matter of measured position. Human observation occurs on the surface of a planet orbiting an average star, located within one spiral arm of a typical galaxy. This location is neither central nor exceptional in physical terms. It is simply where measurement happens. All observations of cosmic scale originate from this position. Telescopes, detectors, and instruments are built here and receive signals that arrive after travelling across space for varying lengths of time. The perspective is local, but the information is not. Light carries data from distant regions without regard for where it is received. Scale remains objective, even though observation is situated. Human timescales are short compared to cosmic ones. A lifetime spans decades. Recorded history spans thousands of years. Even the longest-running civilizations occupy a fraction of 1,000,000 years. Against the backdrop of galactic or cosmic timescales, these intervals are brief. This does not diminish them. It simply defines their duration within a larger temporal structure. The same applies to physical scale. Human-made structures are measured in meters or kilometers. The planet itself spans thousands of kilometers. These scales are appropriate for human activity and perception. They are not intended to match cosmic dimensions. Each scale supports different processes, governed by the same laws but operating under different conditions. Observation allows movement between these scales without requiring physical travel. By receiving light and measuring its properties, humans access information from regions far beyond direct reach. This ability does not change scale, it bridges it. Measurement acts as a connection between local experience and distant structure, without altering either. The methods used to understand scale do not depend on human uniqueness. They rely on mathematics, physics, and repeated observation. Any observer, located elsewhere in the universe with similar tools, would construct a comparable framework. Scale is not centered on the observer. It is revealed from the observer's position. Placing human observation within cosmic scale provides orientation rather than conclusion. It shows where measurements originate and how far they extend. It clarifies that understanding does not require physical presence at every scale. It requires consistency, patience, and careful interpretation of signals. At this point in the exploration, scale no longer needs to expand outward. The largest distances have been reached, and the patterns governing them are established. What remains is a gentle return, not inward through dramatic reversal, but toward familiar regions of space, maintaining continuity. In the next section, attention will gradually narrow again, easing back from the larger structures toward nearer cosmic distances, allowing the sense of scale to settle rather than conclude. After reaching the widest measured distances, the sense of scale can begin to narrow gently, not by retracing every step in reverse, but by allowing attention to move back toward nearer regions of space. This return is not a summary and not a conclusion. It is simply a shift in focus, guided by the same calm structure that carried the exploration outward. From the largest observable patterns, attention moves first to the regions where structure becomes more distinct again. Filaments and clusters give way to individual galaxies that can be named, measured, and compared. Their shapes, sizes, and motions remain stable, even as they continue their slow evolution. At this distance, galaxies are no longer points in a network, but extended systems with internal structure. As the view narrows further, the Milky Way returns as a familiar frame. Its spiral form, its disk and halo, and its steady rotation provide a sense of orientation. The galaxy is large, but it is no longer abstract. Its scale has been established. Its dimensions are known. Its motion is measured. It occupies a defined place among many similar systems. Within the galaxy, attention naturally drifts back toward the regions where stars are separated by a few light years rather than millions. Interstellar space reappears, thin and quiet, filled with faint gas and long distances. The separation between stars feels wide again, but no longer extreme. It fits smoothly into the framework already built. The solar system then becomes a distinct structure once more. Its size is small compared to the galaxy, yet complete in itself. Planetary orbits, the outer belts, and the distant cloud of icy bodies all remain clearly defined. Distances shrink from light years to astronomical units, and motion becomes faster and more immediate. Nearer still, Earth's orbit around the Sun provides a steady rhythm. The timescales shorten. Light takes minutes rather than years to travel. Space feels closer, not because it has changed, but because the scale of attention has changed. The structure remains the same, only the level of focus shifts. Returning in this way does not undo the understanding of large scale. Instead, it places smaller scales back into context. Earth does not become larger. The universe does not become smaller. Their relationship simply becomes familiar again, grounded in measurement rather than distance alone. This gentle narrowing allows the mind to rest within a known frame. Scale no longer expands or contracts actively. It stabilizes. The universe continues to exist at every size simultaneously, and attention can settle where measurement is closest and most direct. As this settling continues, there is no need to hold the entire structure in awareness. The framework remains intact on its own. Understanding does not require effort to maintain. It stays present quietly, supported by the continuity of physical law. In the final section, the motion will ease further, allowing the idea of scale to remain open and ongoing, without closure or emphasis, preparing for rest without interruption. With attention now resting closer to familiar regions of space, the idea of scale no longer needs active expansion or contraction. It can remain present as a quiet background structure, supporting everything without demanding focus. Distances from the smallest to the largest continue to exist simultaneously, whether or not they are being considered. The universe does not require constant attention to remain ordered. At this stage, scale becomes something steady rather than directional. Earth continues its rotation. The planet follows its orbit. The Sun moves with its neighbouring stars through the galaxy. The galaxy itself maintains its slow rotation within a larger cosmic environment. None of these motions depend on observation. They continue with the same regularity regardless of awareness. This continuity is one of the most stable features of the universe. Processes do not pause or accelerate based on scale. Each level unfolds according to its own timing, shaped by distance, mass, and interaction. Small systems remain active and responsive. Large systems remain slow and persistent. Together, they form a layered motion that never needs to resolve into an endpoint. There is no final distance where scale stops being defined. Measurement ends where observation ends, not where structure ends. Beyond the observable universe, expansion and organization likely continue, governed by the same physical principles. The absence of observation does not imply absence of order. It simply marks the limit of available information. Within observation, everything remains connected through consistent laws. Gravity, motion, and light operate without interruption across all measured distances. This consistency allows understanding to remain stable even as attention softens. There is nothing that needs to be held tightly in mind. The framework supports itself. As the sense of scale settles, it becomes less about numbers and more about relation. Each distance fits where it belongs. Each system occupies its range without conflict. There is no compression, no urgency, no demand to grasp more than what is present. At this point, the exploration no longer moves forward or backward. It rests. The universe continues its motion, layered and continuous, while attention can remain still. Scale is no longer something to be followed. It is simply there, extended in all directions, quietly sustained. In the final moments, nothing new will be introduced. The continuity already described does not need reinforcement. It can remain as it is, supporting a calm transition toward rest. The scale of the universe does not conclude, and it does not resolve into a final frame. It continues beyond observation, beyond measurement, and beyond attention, while remaining governed by the same steady principles that apply everywhere. What has been described does not need to be remembered in detail. It exists independently of recall. Distances remain extended. Motion remains ongoing. Light continues to travel. Systems continue to orbit, drift, and evolve at their own pace. There is no moment where this stops or completes. The universe does not arrive anywhere. It simply continues. At rest, attention does not need to follow these motions. Understanding does not require tracking every scale at once. The structure remains intact without effort. The framework holds even as focus softens. Nothing closes. Nothing resolves. The continuity remains open, steady, and unforced. everything flows, sleep in that motion.